Hi everyone, welcome to the CEE122 recitation for the homework 12. So in this recitation, I already prepared my PDF solution here to just save some time so you don't need to wait me to write down all those equations. But instead, I will have this pre-written solution with me, and I will explain how I solve it and the logic behind those solving steps. So let's get started. In this problem 10.59, we have a fluid given the situation, given the condition shown in this diagram. We want to solve for the flow rate. And here on the top, I ran down some information extract from the problem and this diagram, which will have the diameter of the pipe equal to 8 cm and the load density is equal to 800 kg per cubic meter, and the viscosity is equal to 10 to the power of -6. And here we assume the alpha and alpha 1 and alpha 2, there's no loads in this pipe, so that we're equal to 1. So first we will adopt the energy equation that I write down here, which is the energy equation you have used for many times. So so after we have to write down this equation, we can then further plug in the information that we have from this problem and to solve the unknown. So alpha 1 and alpha 2 is equal to 1 according to our assumption. And the pressure we already know is 150 at this point 1 and 120 kappa at this point 2. So 100, and because we want to use the correct units to apply the energy equation, so here we have to convert kappa into pa. So here is the 150,000 pa, and this is 120,000 pa for point 2. And gamma here is equal to rho times g. So rho is 800 and g is 9.81. So we can fill that in for both sides of this energy equation. And we have the velocity term, and we assume the datum to be 0 at this point 1. And to that, we have the corresponding C2 equal to 3 meter, because the slope at this pipe is 1 to 10. So we have 30 in length, therefore we have the 3 meter change at the vertical direction. And finally, we have this head loads at the right hand side. And because the diameter of this pipe did not change along this distance, therefore we know that the velocity at this point 1 and point 2 will be equal to each other. Therefore, this entire energy equation will only have one unknown, which is this head loss HF. So these two velocities will be cancelled out. And to that, we can solve this friction head loss that is equal to 0.823 meter. So after we have these, we want to identify or calculate this factor F. And according to figure 10.14, we need these two information to find this factor F in the figure 10.14. Therefore, we simply plug the information into these two equations accordingly, and remember that the friction head loss HF here is equal to 0.823, which is the number that we just solved in the previous step. And we do the same thing for the relative roughness, Ks divided by D. And for the Ks value, you can look it up based on the material of this pipe. And in this case, equal to 1.5 times 10 to the power of minus 4. And this entire relative roughness will equal to 1.9 times 10 to the power of minus 3. And according to the figure 10.14, the factor F will equal to 0.025. After that, we can apply the equation for the friction head loss, which is the equation, again, we have used it for many times. Now, we know HF, and we also know the factor F. And we know the length of the pipe, we know the diameter, and we know the G. So the only unknown here will be the velocity. And to that, the flow rates, which can be calculated by the velocity, can be solved by using this equation. Then the next step is to isolate this V, the velocity, from this friction head loss equation. After that, you simply plug in all the numbers that we solved in previous step and the information of this pipeline into this equation, and then you can solve the velocity is equal to 1.31 1.312. So yeah, this is 1.312. Okay, we have missed some points here. Okay, but now you know it is 1.312. After that, you have the velocity, you times the cross-section area, then you will get the flow rate. So the cross-section area, the velocity is 1.312 as we saw in the previous step. Then the velocity is equal to pi divided by 4 times the square diameter to the power of 2. Okay, and diameter is equal to 0.08 meter because the diameter is 8 centimeters. So we need to convert the unit first. Then we can get the flow rate is equal to 6.59 times 10 to the power of minus 3. Now let's move on to the next question. 10.60. We have a pipeline is to be designed to carry crude oil with a discharge of 0.1 cubic meter per second and a head loss per kilometer of 50 meter. So we want to find the diameter of the pipe that can maintain this flow, as well as the pump power that can overcome the head loss during the delivery. Okay, so again, we write down some basic information for this problem. The flow rate is equal to 0.1 cubic meter per second, and the head loss is 50 meter per kilometer. The Ks is equal to 0.046 millimeter, and that is because we have a steel pipe, and this number can be found from the table 10.4. And the specific gravity is equal to 0.93, and the viscosity is 10 to the minus 10 to the power of minus 5. Okay. So in the next step, we want to solve the diameter of the pipe. So according to the Darcy-Weisbach equations, which is this friction head-loss equation, we can solve this diameter. So on the top line here is the original friction head-loss equation that we often use. Then we can substitute this velocity into the flow rate. So velocity is equal to the flow rate divided by the area and the cross-section area. So if you plug that in, you will get this second the equation in the second row. Then after that, you can further substitute this area into the expression of the diameter, and you will get this new term in the third row. So according to these equations, you can isolate the diameter to the left-hand side and put the rest of the term in at the right-hand side. Then you got this equation. So next is the triangle, the iteration process. So first you can assume a factor F equal to 0.015. It doesn't matter which number you start with, but you just get a number, and then we can iterate, we can improve the accuracy of this factor F through the iteration process, and I will show you how. So after you assume this factor F, you can plug into this equation that we just derived in the previous step. And for other variable, they are all known variable. The length is assumed to be 1 kilometer, that is 1,000 meter. And we have the Q equal to 0.1 to the power of the 2, and G is equal to 9.81, and pi squared is pi squared. Then the HF is 50. And why now you kind of know why we assume the length to be 1 kilometer, because we want to use 50 for our head loss. And according to the problem itself, it says that a head loss per kilometer is 50 meter. So that's why we want to use the length equal to 1,000 meter here. Okay, so after that, you will get the diameter is equal to 0.19 meter. Then we want to see if this is accurate, so you can recalculate this factor F and try to compare with the previous iteration, see whether these two F factors are close enough to each other. And to do that, we will need to we can do the following. You can calculate the Reynolds number using this equation, and all the information you already know: Q, pi, diameter, and this viscosity. Diameter is the one that we just solved, which is equal to 0.19. Okay, in this case, the Reynolds number will be equal to 6.7 times 10 to the power of 4. Then you can calculate this factor F using this equation that is shown on the screen here. So similarly, you plug in all the information back into this equation, then you will get that F is equal to 0.021. So now you can see that these two F, our original assumption is 0.015, which is deviates from this 0.021. So these two F have not converged yet. Therefore, we can apply this new eighth and do another iteration to further improve it. So apply the same equation for the diameter, plug in this new eighth, you will get the diameter is equal to 20.3 centimeter. And again, you use this new diameter to calculate the Reynolds number and plug in this factor eighth equations to solve it and to check it whether it's converge. Okay, so after 2, 3, or 4 iteration, you will find a close enough factor eighth, the converge factor eighth. Then you can select the diameter that's solved in that iteration. And in this case, D will equal to 22 centimeters. Okay, so generally we'll apply this iteration process. Usually 3 iteration or 4 iteration, you should get a converge number for this factor eighth. Right, so after you get this diameter, we can start to calculate the power using this power equation shown on the left hand side. You know the flow rate, you know the gamma, and you know the head loss. So basically just plugging all the number into it, and you will get this power has to be 45.6 kilowatts per each kilometer, because remember that we have 15 meter head loss per kilometer. Okay, let me add on something. So now we have the power, but let's just go back to this diameter parts a little bit more. So I skip one step. So after you find a stable value for the eighth, then you find a stable diameter, and in this case it's 20.3 centimeter. But because the allowable available pipe diameter are 20, 22, and 24, so you have to select the next larger one than the one we solve using this iteration process. And in this case, the D has to be the 22 centimeters one. Cool. Okay, now let's move on to the next one. In this problem 10.71, it's fairly straightforward because we want to solve the power that this pump needs to supply to this pipeline to pump the water from the lower, not the water, pump the oil from the lower reservoir to the upper reservoir at a rate of 0.3 cubic meter per second. And we also need to plot the HGL and the EGL line for this system. Right, so again, similarly, follow same step, same procedure. We write down the basic information for this problem on the top right corner. The diameter equal to 30 centimeter, flow rate equal to 0.3 cubic meter per second, C1 and C2 is equal to 100 and 112 meters respectively, and the length of this pipeline is equal to 150, though it's 940 kilogram per cubic meter. Viscosity is equal to 10 to the power of -5, and its Ks is equal to 0.046 millimeter. Same according to the table 10.4, and because this is a steel pipeline, so you will find the corresponding Ks in this table 10.4. Okay, so the reason why we have pump is to overcome the energy difference between this lower reservoir and the top reservoir. So we will need to apply the energy equation. So we first write down this energy equation shown here. And similarly, we assume that the alpha1 and alpha2 is equal to 1, and then we plug all known information into this equation. The point 1 is on the lower reservoir and the point 2 is on the upper reservoir, and both of them are open to the atmosphere, so you can simply cancel this pressure term. And we and also we don't have the velocity at these two reservoirs, so you can further cancel out these two velocity terms. Z1 is equal to 100, and HP is the energy provided by the pump, and Z2 is equal to 112, and you have the summation of the minor halos that can be collected and written in this form, which is the velocity term times the Ke plus F times L divided by D plus Ke, which is the entrance and exit halos. Right? Okay, so you move these 100 to the right hand side and you will have this 12, and you plus the minor halos that can be returned in this form, and you can find this Ke and K capital E equal to 0.03 and 1 according to your textbook. So the only term that we don't know yet is this factor F. We know the things, we know the diameter, but we don't know this factor F. So we need to solve that. Okay, the velocity can be calculated easily using the flow rates and the cross-section area, and as I show on the screen here. So the velocity term here will equal to 0.9181. So let's go back to this factor F. To solve that, we will need to use the Moody diagram. And to use the Moody diagram, we will need to calculate the Reynolds number and the relative roughness using these two corresponding equations. And again, after you write down this equation, you can simply plug all the information that we got at the top to this equation, and you will get the corresponding value for the Reynolds number and the roughness, relative roughness. After that, you can apply to the Moody diagram and solve for this factor F, and in this case, F is equal to 0.0165. So after we have this factor F, you can plug it back to these energy equations to calculate for the energy the heat provided by the pump. So I write down the equation for the pump and plug in a number down here as my cursor. And then you can just calculate this pump head that it will equal to 20.52 meter in this case. After you solve this pump head, you can apply the power equations. Simple enough. Q times load times the pump head. All those information you already know. The flow rate is equal to 0.3, and the gamma is 940 times 9.81, and the pump head, we just solved it, is 20.52. So the power is equal to 56,770 watts, and that will also equal to 56.8 kilowatts approximately. Good, so we can move on to the next one. In this problem 10.72, we have a similar goal. We try to find the commercial grade plastic pipe size for this penstock, given the information provided by this problem and as well as in this diagram. So I just write down all those information on the top right corner here for you. The flow rates need to be 2 CFAs. The H, which is the height of the upper reservoir, is equal to 34 feet, and the friction handle is equal to 3 feet. Length of this pipe is 87 feet, and the viscosity is equal to this number. Again, according to the table 8.5, you can find the corresponding viscosity number there. So in this problem, you will encounter several unknowns altogether, so we need to collect different equations and solve them simultaneously. So the first equation that we can use or can write down is the friction halo equation, which is this Darcy-Weisbach equation here. And the second equation we can use is the resistance coefficient, and that is equal to this, which I have already written on the screen. Also, we will need the Reynolds number, that is equal to V times D divided by the viscosity. Also, we have this flow rates equal to V, the velocity, times the cross-section area, which is equal to pi times d to the power of 2 divided by 4. So after we have these four equations, basically you can solve all the variables all together, and you can get that F is equal to 0.01448, the velocity is equal to 9.028, D is equal to 6.374 inch, and the Reynolds number is 289,000. Okay, so because we have to select from the commercial grade plastic pipeline, therefore we just need to select the one that is larger than the diameter that we solve, and in this case we have to choose the 8-inch pipe in this case. In problem 10.82, we have a system look like this figure here. Both pipes in the system shown have an equivalent sand roughness Ks of 0.1 millimeter and a flow rate of 0.1 cubic meter per second, with diameter 1 equal to 12 centimeter. Length of this pipe 1 is equal to 60 meter, diameter 2 is equal to 24 centimeters, and the length of this pipe 2 is equal to 120 meter. And we want to determine the difference in the water surface elevation between these two reservoirs. Okay, so when you see this system, you should come up with energy equation. And yeah, so again, yeah, we do need to apply the energy equation to solve this problem. So we know the reservoir, the height of the reservoir difference. If you simplify the equation, the pressure turn is equal to 0. You don't have the velocity at these two reservoirs, so you don't have the velocity term. So the height change, which is z1 minus z2, is actually equal to the headers during this transportation in this pipe 1 and pipe 2. Okay, so that's our goal. We want to solve this. The difference between these two reservoirs, the water surface of the reservoir, this Z1 and Z2, is the value that we try to solve. So we actually need to calculate the total halos that we have during this transportation in pipe 1 and pipe 2. And until that, we will need to calculate this H factor for this pipe 1 and pipe 2, because there's the friction halos happen in these two pipelines. That's why we need to calculate that. To calculate that, we will apply the Moody diagram to find out these two factors F for pipe 1 and pipe 2, and to that you will need to calculate the relative roughness and the Reynolds number for these two pipelines. And I show you the equation here, and you can simply just apply the equation of the Reynolds number and the relative roughness to calculate these two terms for two pipe. And then you apply the Moody diagram to find the factor F for pipe 1 and pipe 2, which is equal to 0.019 and 0.017 respectively. Then you can go back to the energy equation and expand the summation of the halos into the friction halos at this pipe 1, the abrupt expansion between pipe 1 and pipe 2, and the friction halos at this pipe 2. And at the same time, you will also need to consider the head loads due to at this entrance location, and also the head loads at this exit location. And how to calculate that? You can go into the textbook and can find the corresponding equations there, which have more explanation, but here I just show you the end equations and calculations for all those terms, showing this equation here, which is at my cursor here, okay? And after you write down the equation, you can simply just plug in the number, and you should be able to guess that the difference between the Z1 and Z2 is equal to 44.5 meters. Cool. So let's move on to the next one. For this last homework problem, 10.85, it's basically follows a similar procedure as the previous problem, but in this case, we already know the elevation at this lower reservoir, which is equal to 110 meters, and we want to solve the elevation for the upper reservoir. So basically, it's almost exactly the same procedure as the previous one. And from the table 10.4 and table in the appendix 5, you can find the coefficient for the roughness case and the viscosity number, as I show on the top, upper right corner here. So again, we need to calculate, we need to use the energy equation to build up the relationship between the upper reservoir and the lower reservoir. And because they don't have the pressure term, they don't have the velocity term, so the only reason that causes the difference in their elevation is due to the head loss. Therefore, we need to calculate the head loss, and so to that, we want to calculate the friction head loss in the pipe 1 and pipe 2. To that, we will apply the Moody diagram, which you need this relative roughness and the Reynolds number in order to use the Moody diagram showing the figure 10.14. So the equation is right on the screen here. You plug in the informations correspondingly for pipe 1 and pipe 2, and you can calculate the velocity using the equation, the flow rate divided by the cross-section area. And you know the diameter, so you should be able to calculate this area, and you also know the flow rate that is given by the problem is equal to 0.03. So the velocity is a known variable that is equal to 0.955. And after that, you can also calculate the velocity for the second part of the pipe. So you can use those two velocity to calculate a Reynolds number for both sections of the pipe. After that, you apply the Moody diagram, and you can find the factor A for both sections. So one is 0.022 and one is 0.024. So this is the simple, in the next line of equation is the simplified energy equation. As I have explained it earlier, we don't have the pressure term, we don't have the velocity term at this reservoir. So we have this equation here. The difference in the height of these two reservoirs is equal to the head loss. And you can further expand this head loss to the friction head loss and other minor head loss that you need to consider for the entrance to this pipeline, the string contract section between these two pipelines and the exits to the lower reservoir. So after you expand that and you can find the corresponding equation in the textbook, I will refer you to read your textbook, or at least to find out the equation that you should use to solve this problem in the textbook. Here, I just show you the end result. So you can simply expand this head loss term into the equation that I show on the screen here. I encourage you to verify that in textbook, but you should already know that if you do your homework. And then you can simply plug in a number using the friction, using the factor F that we solve here. And we know that the Z2, the elevation of the lower reservoir, is equal to 110. So the entire term after the calculation, it's equal to 114.2 meter. So basically, the same procedure as the problem 10.82. So yeah, this is the recitation for this homework 12. If you have any question, you can just email me and I can do my best to help you to solve your question. I mean, answer your question.